Let's make sense of this.
Let's make sense.
Sense makers.
Hey Ken, welcome back to the Alteryx Expert Exam Regression, and this series is going to be around practice.
Thanks, Matt, for having me back. Look forward to our session today. It's going to be a little bit different, I think.
Yeah, I think it'll be interesting, and this is going to pair well with the classification chapter. These kind of go hand in hand. In terms of the way the Alteryx exam works, the way you're going to approach these problems is going to be very similar. The only thing that's different is regression problems are going to be solving numeric results. You're predicting something that is like a numeric, either integer or continuous variable, like a home sale price or a lap time amount, some sort of numeric output. Classification is more about grouping, so either yes or no or low, medium, high risk. So it's really just about what your target variable is, what you're trying to predict. That's going to be the distinguisher. But in terms of mechanics, the way you're going to solve this problem is going to be very similar. So if you do these, look at both of these chapters together because a lot of the concepts are going to overlap. So I give a couple recommendations here on some weekly challenges you can do in terms of how to practice and getting comfortable with the tools, getting comfortable with the individual regression models, as well as the score tool is going to be essential for what you're going to want to do. But beyond just doing practice, and like I list out some of the models here that you're going to want to be able to be familiar with. And by familiar with, I mean just drag it onto the canvas, open up the one tool example, plug data into it, run it, and just see what the output anchors look like. Sometimes you're going to get a report, you're going to get a model output, and just kind of see what it gives you. Because it depends on what the exam question is going to be. Sometimes they're going to ask you something about the report or the formula that was used to generate it. Or it's going to just ask you simply about the metrics that come outside of it, like root mean square error, for example. So just understanding these tools are just going to be very helpful in terms of understanding what types of things could be in scope for the regression. Now, it's going to sound overwhelming, and I wouldn't focus so much on memorizing all these tools. This isn't really a memorization type question. This is more of like, just be familiar that these exist, take some time and just open up the one tool examples and just click around, run stuff through them, and you're going to notice they're going to functionally work very similarly. The only thing that's different is the algorithm inside of them is different, but from like a connecting your data to it, that part's going to be the same. And just knowing what the names are and some slight configurations on if you have to configure it, that's where it's going to be relevant. But I wouldn't spend a ton of time researching like, 3 paragraphs deep on what a spline model is or a stepwise, all the nuances of it, other than just being aware that it exists. And if you're asked to use that, you just kind of know where to find it. So Ken, any other thoughts on kind of working with like the Alteryx kind of predictive tools in general, especially like either for regression type or classification type problems?
Well, for me, one of the things that I like to do is take an example that I'm familiar with and then run it through different types of algorithms just to see you're putting in the same numbers, you're putting in the same values, but you're getting different forms of output. Not every model, every type of regression model gives you the same type of output. Sometimes you get area under the curve, sometimes you get root mean squared error, sometimes you get other things. But really, always the goal is to be able to make some predictions. So it's good to be thinking about that as you go into it and you say, okay, so here's my incoming data. I want to be able to predict whatever it might be, X, Y, Z. I want to predict this. So be thinking about that and then let Alteryx do the work and then look on the output side. What are you getting? Sometimes you're not going to understand everything. You're not going to understand every type of output. So just when you find your weaknesses, just take a look at them. See, understand what is area under the curve, what is root mean squared error? How's it calculated? Fill your background in a little bit there before you get to the exam so that you're not feeling that panic that comes with, oh, I don't even know what that means kind of thing.
Yeah, I think that that's a valid point, and I think a decent amount of this, especially for the predictive type problems, I think people can feel very overwhelmed or intimidated if they don't do data science in their job or as a hobby. Whether that's as a data scientist like yourself or a citizen data scientist, I think the topic just scares people and it can make people feel uncomfortable. And that's understandable. And I think it's very reasonable. However, the way Alteryx is going to ask you about these tools is not as intimidating as it seems. And so I'm going to walk you through that here. So I've got Alteryx Designer opened. So one of the things I said at the top was clicking on the tools and just being able to open up an example. So I opened up the score tool. The score tool is essential. This is going to be at the end of the day, what you're going to need to do to be able to predict a value. The other tools, like let's say linear regression, gamma regression, forest model, decision tree, these are all kind of in the same camp. These are all models that you basically connect data to and you have it generate a prediction. Score, at the end of the day, is what you're going to take and either apply to net new data, data that it hasn't seen yet, or data that you've maybe held out or are filtering out to then take what the model is predicting and then applying the model object and it's scoring it. It's giving it a prediction. And this is the real, like, what brings it all together. So if I just open up the score tool, I get a very simple example. I get a data set that's got donations, it's got a degree, first year, last year. So this is basically like education. This is explaining for people who is likely to, let's say, donate. And they look at a bunch of different features or columns. So were they an undergraduate? What was their first school? What was their last school? How many years ago did they attend here? What, gender? Do they have children? Do they have parents? Do they have a spouse, etc.? So it has all these different attributes, whether it's a yes, no, or a numeric input. And so you're just going to have a mixture of those. The next tool is probably going to come up quite often. If I would most likely expect it to. There's one exception to the rule, but the general rule of thumb is create samples. And what you're going to want to do with this tool is it's going to ask you to say, I want to use, let's say, 70% of my data as a sample to estimate, and that's what I'm going to train my model on. And then let's say I'm going to have 30% for validation. And what this is going to do is it's going to randomly take 70% of the data, put it into this E anchor. 30% is going to go to this V anchor. The thing is, this can sum up less than 100 as it's noted here. So I could do this as 60, let's say. So that leaves 10. 10 will go into holdout. So what you can do is you can say, I want to evaluate and train my models on 60% of the data. I then want to validate and do, like, let's say, a model comparison on data that it hasn't seen yet. So are these model objects overfitting? Is it memorizing the patterns? And how well does it do on data it hasn't seen yet? And that's the real thing with data science, because quite often you're looking at problems where you don't know what your future data is going to look like per se, and you want to see, how does this model handle data it hasn't seen yet? How robust is it going to be? Versus if you just give it everything, it's just going to memorize the pattern. But how does it do when it handles data that isn't in that sample? So that's what you're going to want to acknowledge here. Good explainer, you got to sum up to 100%. Then they give you a sample tool. So they give you a forest model. And so these tools are going to be in the predictive category. I click on forest model, I can open an example, and then you get more details about kind of what it does. So in this case, they want you to do, your target variable is donate, yes or no. But you don't have to necessarily do that. You can do any type of field you want. So this would be like a classification type one, but you could do something that would be if I were to open up a linear regression, it would pick something that would be numeric. And what you can ultimately do, and I think the best way to practice these types of problems, is to just kind of open these up, these one tool examples, just hit the run button. You can read the explanation here, but then what you can do is you can combine multiple tools and get a sense of a tournament of models. Because quite often you're going to run into a scenario where it's going to ask you, well, you have this data. We want you to test, let's say, decision tree and forest model and linear regression and neural network. And we're going to give you a metric like root mean square error and say, pick the model that has the best root mean square error based on 60% of the data that you evaluate, and then 30% you validate on, and then 10% you hold out. A long way of basically saying, run a tournament of models, figure out which model does best on this data, and then pick that model and score it. So mechanically, the way it can work is for, let's say, linear regression. I have a data set. It's on baseball teams. I've got the team, the games, the number of wins. I've got a bunch of metrics on, let's say, runs scored or hits, etc. So just looking at the one tool example, let's say I want to predict runs per game, R_G. And then I'm going to train it on slugging and OPS and go, how much can we predict runs scored based on these two baseball metrics? And so what I can do is I can do that. This particular example is doing a nested test, which is basically comparing the same model itself, a linear regression, but one has more features than another. So in this one, it's got slugging, OPS, and games and wins. The smaller model, or the simpler model in this case, just has slugging and OPS. Nested test is one of those examples where you can actually compare the two and go, is the more complicated model or the simpler model more effective? And what they'll do is they'll just say, removing these variables, games and wins, did it have a statistically significant outcome? If it did, then that means you will need to keep your more complex model because those values were important. But if they weren't important, then you can just keep the simpler model. You don't necessarily need to memorize that per se, unless they give you that example, but then that's just kind of how nested test works, and you can just go on the explainer here on how it works. But it's not necessarily about knowing how nested test works. What I can do is, let's say I don't want to do a nested test example, but I want to take this data and I want to run a tournament of models. So what I can do is I can take linear regression. Let me just go ahead and bring on boosted model. And let's say I'm going to do the same thing. I want to predict runs per game. And I'm just going to pick the same metrics. And this is the key. You have to go apples to apples. The value that you're predicting and then the features. So I'm just going to call this boost. I can grab a forest model and do the same thing. Up here, I'm just giving it a name. This will just make my life easier. So because these things can take a long time to run, I just need to remember which model object was what. So I just come down here. I'm just going to look for runs per game and then look for my two metrics, slugging and OPS. And then what I can do is I can just grab a union tool. And union the O anchor. The O stands for output, model object output. The R stands for report. So as I had said earlier, the R is representing the report itself. So when Ken was talking about some of the key metrics, you can get some of the tables down here. And this is stuff that you can Google and get a better sense of what is the F value or the degrees of freedom or standard error or the estimate. This will give you some of those metrics that you might get asked about or have to evaluate on the exam. And these are the things in the report tab or in the I tab, depending on the anchor output options, that you can just evaluate. So one of the key metrics. So if they ask about adjusted R squared or mean absolute error or MAPE, mean absolute percent error. It'll give you these values. So you can use these different outputs, understand how they work, and so if you do get a question about which has the best root mean square error, you can compare the numbers. But sometimes you can do something like this. So let's say I want to do a model comparison. I want to take my model comparison tool. I want to take my model objects in the O anchor, connect it to my M, that's for model, and then I can connect the rest of my data to D. So in the prior example, we had shown about create samples, so I'm just going to do that here. Nice little Alteryx trick. If you click on a tool, you can always just right click and do insert after, and then that way you don't have to like reconfigure everything. So what I've got here is I've got all this. It's a little bit of a mess. I'll just organize it. Let's just change the outputs of these to the evaluation, and then be able to configure the tool. So you can just always click on these lines, right click, and just change this. This is just kind of helpful ways to reconfigure your tools without having to kind of delete, reconnect. So let's give it a 70. Let's give it a 30. So the idea here is I'm taking 70% of my data, going to the E anchor, and it's going to go to all these models. I've got my validation, which is getting 30% of my data. And then at the bottom, I've got my random seed. This just helps randomize your data, but they might tell you to change the number. So in the instructions, they might say set your random seed to 5. It just exists. It's here. Just make sure that if you need to change it, you change it. If they tell you what your estimation, your validation is, you just set those up. So I can connect my data here. I can just right click on this tool and just do the add all browses, or Control Shift B, whichever you prefer, and I'll let it run. So this is kind of like Alteryx's approach to, let's say, running model objects and doing a tournament of models. Ken, have you used Alteryx in this way to kind of do a tournament of models, or ways to evaluate different models and see how they perform against each other?
Yeah, Matt, a few years ago, my son Colton was in college, and he got entered into a couple Kaggle competitions, and we were using Alteryx. He was using Alteryx, and so I helped him with this. I said, let's try, because you don't know a priori which model is going to do the best. So we essentially did what you're doing here, picking different models, trying different things. Each model has different configuration settings. So once you begin sort of zeroing in onto the best models, then you can begin sort of optimization studies on that particular model by changing some of the parameters. And that's what we did. What was interesting is in that class, there were, say, 20 or 25 students, and you get the scoreboard. And we were never able to crack, say, in first place, but we would be maybe the top 3 or 4. But there were some students that had some advanced technologies that they were able to use, which were beyond the capabilities of what we had here. Don't know what they were, but they would always score a little bit better than we did. And that's sort of the secret sauce of data science at times. Feature engineering is one approach where you're using so many of the different variables, and you're trying, maybe they have good feature engineering code that would identify the most important and salient inputs to the model. And we didn't have a feature engineering code at the time. So those are the kinds of things that can happen. But essentially, yeah, man, I've done it this way, and I did it also in my own work with my global warming simulator. So it's good technique.
So I'm going to run this here. For whatever reason, the boosted model was being fussy, so I've removed it, and I'm just going to rerun this. And so when I get to the point where the model is, or the workflow is done running, right now I've only got 30 records, 70% are going to evaluation, 9 are going to validation. I get some internal error, but it doesn't functionally prevent me from doing the problem. So Ken, when you see the models listed here and these metrics, how would you interpret something like this?
Well, the lower errors are typically going to be better. So you have root mean squared error, you have mean average error. You have probably right now on my screen, I have you covering some of some of the output, so I don't see them all. But you're generally looking for the lowest error to find the best model. So linear regression right now looks to be outperforming forest.
Sure. So we've got the root mean square error is lower, and that's closer to zero, right?
Right.
Zero's functionally perfect, but if it's actually zero, that's probably a problem because there's maybe overfitting or some other
Yeah.
stuff. It should never be zero, right?
Zero. Right.
But closer to zero. The correlation you actually want higher, right? Closer to one.
Yep.
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 And then mean average error, MAE, closer to zero. Mean percentage error, closer to zero. Mean absolute percentage error, closer to zero. So if the question said, which would you pick and why? Ken, in this case, you picked linear regression, and why was that again?
Lower overall error, higher correlation. Um, that would be the simple explanation. And so, as I was saying earlier, then I would, in this case, take a look at linear regression, take a look at what are other options might there be in the configuration of that to further improve the predictive capability of the model.
Sure. So if I come down to customize, you have the ability to do some customization if needed. You do have the ability to do some cross-validation with folds and trials and a random seed. And then for the plots, you'll just see the output. So if you do need to go under the hood and customize it and maybe fine-tune it, and when you were talking earlier about optimizing model objects and feature engineering, like that was kind of the secret sauce, potentially you might need to know how to do that here. And so if you do, for the linear regression, for example, you just come down to the bottom and go to customize. Otherwise, if you just take the values as is, you're good to go. So I did notice that one did have an extra attribute, so I just want to make sure I'm comparing apples to apples. So it's just slugging and just OPS. And then I'll just rerun it again. And while that's running, a key on these types of things to practice and understand for the exam is that this is actually running relatively quick. The reason it's running relatively quick is because I have two model objects that I'm using. I also have a data set that's 30 records. But if you have a data set that's 10,000 records or 100,000 records, and you've got 4 or 5 model objects, well, this could take a long time to run. And so one of the things you want to do about practicing is making sure you follow your instructions, do what you need to do, and then if you get to a point where you're happy with your result and your model objects, you might want to just cache your results, so then that way you don't have to rerun this whole thing from scratch. Now, making sure I compared apples to apples, it actually did not impact my metrics at all, so I can feel rest assured that in this case, if I just want to do a simple linear regression versus the forest, what did better? I can go with linear regression. So then what I can do in this case is I can kind of highlight all of this. I'll just add it to a new container, and I'll just call it train. The idea is that this is what I'm doing to train my models. I'm just going to move all this stuff out of the way. And then what I can do is then I can just paste this down here. And then let's go, let's take this. And this can then be my run full model. So I just want to keep my linear regression, so I'm just going to delete my forest. I'm going to get rid of the rest of my tools here. Yoink. And then let's just say on the validation, that's going to be the data that I actually want to run this on. So I can run this on my validation set. I can disable my train. Or, sorry, let me do this. I will keep it on my evaluation, so I actually keep the same model object. But for my score, I want to score it on my validation data. So I can take my model output for my score tool, the M anchor here for model, D is for data, and then I can take my data itself, connect it to the D incoming anchor, and then be able to run this. So what I like to do is if I feel comfortable in my model and know what I like, what I'll generally do is I'll just grab a select, connect it to my score tool, and then a browse. And on the first time I run it, I actually won't just run it in that sense. I'll just right click and just do cache and run workflow, because I know that everything I need to do at this point, I know what my model is. I'm evaluating it. I'm running the same logic that I trained it on to then to use to score. I'm using all that same logic. I'm just caching my results because I know everything I need to do at this point happens here. And so if everything needs to happen here, I don't need to worry about all this stuff upstream. We just spent that time looking at a couple different models and then running it through. And so everything I need to do in terms of calculations happens after this select tool. So now I've got my data. I've got my teams. I've got my score, which is predicting, let's say, my runs per game. So let's say the example was, let's look at my team. Let's look at runs per game. We can do this runs per game actual. And then our score at the bottom, which is always going to be your last column, I can just call this runs per game projected. And then let's just do a simple formula and just go, what was our delta? So I can just do actual minus projected. I'll just make it a double. And now I run this and it'll be instantaneous. So now if I wanted to see my delta, I could. And then there could be some sort of any type of question from there. What was your, what was your median delta, or what was the median difference? Which team had the highest discrepancy? All the types of analysis you want to do, you can do from here. So by just caching this, now I can prep my data and do that final leg to answer the question. And the question can be any variety of things based on what is predicted. So the score is doing a projected value of runs per game. I have in my data set my actual value, so I can compare the two results and then be able to then go from there.
Now, Matt, one thing I noticed in your cached results, if you were to go ahead and clear the cache for me for a moment and go back to your model object, your linear regression model object, those same two settings were brought forward.
Yep.
How did that happen like that? Because it seemed like when you connected back to your sample tool that it would have reselected all of them. Did you manually set only those two input fields, or did I just miss that?
So up front, the way it was configured was it was
Yeah.
configured with these tools. But so what I did was I copied
Oh yeah, because you copied it down.
the container down, and the reason
Yeah.
for that is because if you copy multiple tools that have configurations, this is actually how I learned about I think transpose and crosstab, in terms of you want to keep the configuration but not have to do it from scratch. I just highlight all these tools, right-click, copy, paste, and it keeps the configuration of the tool itself, even though I'm changing the incoming connector. So that way I don't have to redo this, which can introduce error. If you have to pick 5 fields, you can accidentally, whoops. Now I'm going to get an answer that could be slightly wrong, and then that way you don't have to worry about it. So yeah, so that's why I like doing this. I do my train container, and then I can do run full model. That's its own container, and I'm just taking the model object, and then the score tool I just keep as is. You do potentially have to be cognizant of this. This is a bit of an advanced concept about if you're oversampling. This comes up when you have, let's say, a data set that is very unbalanced. Like, let's say you've got, 10,000 records, and let's say it's like about like cancer treatments and like cancer positive rates, and only 20 rows in your data are actually positive, but the rest are negative. You're going to want to oversample in that instance, which comes up here. And the reason you want to do that is because you want to make sure that you have a representative share of your yes and no's. The idea being that, like, when you train your model, you want to treat it as if it's almost 50-50. So that way it cares about the features more. Because when you have a disproportionately low feature you're trying to predict, like 20 out of 10,000, it's actually going to do a lot worse if you just compare it like apples to oranges. But when you oversample and get to a smaller amount, like let's say a 50-50, like instead of going from 10,000 and I've got 20 positives, I'm going to actually go down to like 40 records. So it's more balanced. What that'll allow you to do is then the model will be much better at picking out key attributes. And so the reason that comes up is if you do use oversampling, in your score tool, you can just represent that here, do the amount of the percentage that was oversampled, and then what was the value of the field that was oversampled itself, like yes or no, or fatal, non-fatal. Just something to keep an eye out. This is a more advanced thing. It may come up. So just know that it works there, but I would say it's a pretty decent guess that you can just kind of leave this as is. Just leave the base configurations, but if it does come up, you can have this here and just also know these checkboxes do exist in case they give you instructions about doing these options. I think that takes us to kind of where we need to be. So this was a bit of a freestyle example, but I think this is the type of practice that you can actually do. So the weekly challenges that I showed earlier are going to give you structured problems, but I would say have some fun freestyling. Pick these tools, open them up, connect it to the same data set, pick the same features. You can use your association analysis to figure out correlation. Pick out values that have high correlation with each other, run it through, boosted or decision tree, forest, gamma, linear, Bayes' classification, and then neural network, and then do your model comparison, and then pick your best model and score it. So that'll kind of wrap up our topic on practice for regression problems. Ken, I really want to thank you for joining me today. And then coming up in our next video, we'll talk about approach.
It was a lot of fun, Matt. Appreciate it. Thank you.
All right, take care.
Let's make sense of this.
Let's make sense.